Hi everyone, welcome back. In the previous segment, we have learned what the conceptual views of geographic phenomenon in GIS and how they are related to unique GIS models. Specifically, we learned about discrete object view and vector data model. In this segment, we'll explore the second data model, raster GIS model. If you are to examine a geographic phenomenon that occurs across the space, Earth's surface, the spatial pattern is taken with constant field view, meaning data values are available at all locations. Here, the study area or the area of interest is regarded as a surface made up of a near infinite set of data collection points. If these potential data collection points are stored as cells or pixels, this GIS data model is called the raster data model. Raster data model uses a series of equally spaced and sized grid cells that contains a single value. These examples clearly show the general structure of raster data models. A geographic area is covered with cells that has a single unique value, either quantitative, such as temperature, or qualitative, such as land cover class. In raster model, each cell in the same raster file has the same resolution or is at uniform scale. In other words, the same grid data set cannot mix different cell sizes. Also, depending on the cell size, the same geographic entity or phenomenon will have different representations. Let's see the example. Compare the representations between a raster model with one cell. Technically, this is a vector model since it takes the distinctive boundary of the polygon. Okay, then compare the second raster model with the 16 by 16 cells to the last one with the 4 by 4 cells. The same geographic entity, say it is a lake, can be represented with 75 cells versus 5 cells. Of course, the smaller cell sizes allow higher resolution and higher feature accuracy when compared to larger cell sizes, resulting in lower resolution and lower feature spatial accuracy. So which of these two is the vector model? Which is raster? The one on the right is the vector model, which clearly show the realistic boundaries and shapes of geographic objects, while the raster on the left uses cells. Good job. So to compare vector and raster, vector models are more complex due to its topology, and in this data structure, relationships between objects are explicit. On the other hand, raster models are less complex, and so relationships between entities are implicit. Lastly, in addition to vector and raster data models, GIS also uses tabular data that contains non-spatial information. The sample table contains much information about tornadoes from 2008, but clearly it is not a map. This type of table is brought into GIS as attribute. If the table includes a unique ID that represents a location or direct locational information such as XY coordinates, you can bring this information into GIS. In GIS, each column called field shows the information items, while each row called record shows geographic objects such as each county in Colorado or each state in US. The process of connecting or linking the table to a map is called joining. To do so, you will have to have from both tables a common matching column. This common field is called a key. Here from the example, SDUSPS and ABBREV abbreviation contain the same information of two-letter state abbreviation. So joining will return the result of a combined table that has both the attribute table of the map and data table with non-special information. To join tables successfully, it is critical to have matching columns from each table that contain the same information and the same data or field type. Even though the columns have same 10-digit GeoIDs, if the field types are different, joining will not work, and you will have null values in the table. Now, spatial data can be categorized by the measurement level. There are 4 forms of attribute data: nominal, ordinal, interval, and ratio by the order of measurement level. Let's assume we are looking at the data table that contains the information of Asian cities by the average temperature in December and population density. Names of the cities are clearly nominal data, while the rank in population density is ordinal data. These variables can be written in numbers, but they are not necessarily a quantity or magnitude of the item. So you can and shouldn't do any calculations such as additions, subtractions, or multiplications. For example, it doesn't make sense to make a core plus map of driver license numbers or social security numbers, since these are quantities. Interval and ratio data are actually quantity data. The main difference here is the interval data has arbitrary 0, while ratio data has actual fixed 0 values. Let's look at the example. For instance, 0 in Celsius is neither the absolute bottom of the scale nor the same 0 in Fahrenheit. As a matter of fact, 0 degrees Celsius is 32 degrees Fahrenheit and 273 degrees Kelvin. So 0 is relative, arbitrary point in the scale in interval data. However, for ratio data, 0 means 0. So $0 is no money. 0-year-old means not yet 1-year-old, but there's no negative year-old. So the 0 is absolute 0. Let's review the non-spatial data forms. Which of A, B, C, or D are nominal data? Correct. A and C are nominal data. Again, C is written in numbers, but these are not quantity. Then what data form is for B? And how about D? For both B and D, these are, yes, ratio data with a fixed, non-arbitrary zeros. 0 number of household in the census tract means no household at all. Great job. Lastly, another important GIS data is metadata. Simply put, metadata is the data or information about the data. This slide shows a federal standard for GIS metadata, and you can see what information should be included and available to the public. All GIS data Either special and non-special information can be stored in specific GIS file types. As you are quite familiar, shapefile is the main file format for vector data. A shapefile is a single vector data layer. It can only contains either point, line, or polygon, not two at the same time. The other main data format is geodatabase. A geodatabase appears as a file folder for GIS layers, but is actually a single item. In a single geodatabase, multiple feature layers and data tables can be stored to maintain the relationship. This example shows a file geodatabase named isodh.gdb that contains 4 different feature layers, 3 polygons, and 1 line feature layers. So far, we have explored the different types of GIS data models, as well as for non-special data forms by the measurement level. Please review the PDFs and the textbook chapter associated with this video lecture so you can have a solid comprehension of this important component of GIS. Feel free to reach out to me if you have any questions. See you next time.